thought that the line of best fit represents the best prediction for a variable given a parameter. However, this is not necessarily the case. Let's find out why using real-world data. So the first thing we need to do is collect our data. I'm here on nba.com/players, and on this website we can find some information about every player that is currently in the NBA. Specifically, I want to look at height, weight, and position. I have a question for you to keep in your mind through the rest of this video. If you know a player's height and weight, can you have a better guess to what their position will be? So to extract this data, the first thing we have to do is go to Page and press All. This will give us the entire data set. Now this is a small enough data set to where we can go scroll to the bottom of the page and simply copy and paste everything into Google Sheets. If you're working with a larger data set, you might have to use a Python script in order to web scrape the data from the website. After we have the data all highlighted, press Ctrl+C to copy, go to our spreadsheet, Ctrl+V to paste. Now that we have our data within our spreadsheet, the first thing we have to do is clean our data. The reason why is we go to height column, press Control, and press weight column. Go to Insert Chart, Chart Type, Scatter Plot. We cannot create a scatter plot based upon the data as it currently is. The reason why is because of this weight. Every cell within the weight column has this LBS tacked onto it. It's 243 LBS, which represents 243 pounds. We need to convert it to purely numerical data. In other words, we have to remove the LBS from every cell within the weight column. To do this, we press Ctrl+F. We're going to find every instance of LBS, and we're going to replace it with blank. Press Replace All, and now we have a scatter plot that actually works, but it looks a little bit weird along the x-axis. It has 512, 526, 69, 623. The reason why is because Excel does not understand this notation for height, of having feet and inches. To fix this, we have to convert feet and inches to purely inches. So 6'8" is going to need to be 6 times 12 plus 8 equals 80 inches. Now, to convert our height column from feet and inches to purely inches, there's two different cases we have to consider. First is when we have a single-digit number for feet and a single-digit number for inches, such as 6 foot, 8 inches. Second is when we have a single-digit number for feet and a double-digit number for inches, such as 6 foot, 11 inches. The way we can differentiate these two different cases is by the length of the cell. Number of characters in the cell for a 6'8" will be 3. A 6, a hyphen, and an 8. Number of characters for 6'11" will be 4. 6, a hyphen, and 2 ones. So we can say equals if length of the cell of E2 is equal to 3. That's our logical expression. Now we have to input a value if true. We're going to want to take the leftmost character of E2 and multiply it by 12. So that's the number of feet multiplied by 12 inches. And we're going to want to add the rightmost character. So this script right here will take 6, multiply it by 12, and add an additional 8. And if the length of our E2 cell is not 3, that means that it has to be a double-digit inches value, in which case we're going to want to take the leftmost character, multiply by 12, and add the right 2 digits. So this way, 6'11", we're going to take 6 feet and add 11 inches. We press enter and we take the suggestion from autofill. So now 6'8" is converted to 80 inches and 6'11" is converted to 83 inches. So we know we've done it accurately. Now we are going to go down and highlight every cell within this new height column. I'm going to press Control C. We're going to go to our height column, the first of the height column, the 6'8". Going to right click, paste special, values only. And then we can delete that other column. Now you can see that our scatter plot looks a bit more normal. We have every height in inches on the x-axis, and every weight on the y-axis. Now, if we try to plot position versus height with a scatter plot, we see that we come up with something weird. The reason why is because position is not in numerical format. It has alphabetical letters. So we have to convert these letters into numbers so that we can work with the data. The way we're going to do this is we're going to write some pseudocode to help us think about it. If we find a G for a guard, we're going to assume that guards are the smallest players in the NBA, and we're going to assign them a value of 0. If we find guard forward or forward guard, we're going to assign that a value of 0.5. If forward, we're going to assign that a value of 1. If forward center or center forward, we're going to assign that a value of 1.5. And if center, we're going to assign that a value of 2. So that's how we're going to convert all 5 of the possible positions in the position column to numerical values. So now we do Control F, find all instances of G, going to match case and match entire cell contents and replace it with 0. Place all. Now we're going to do the same for forward guard, place it with 0.5. Guard forward, 0.5. Forward, place it with 1. Forward center, place it with 1.5. Center forward, place it with 1.5. Center, place it with 2. And now, if we switch our x and y axes so that we have height on the x-axis and position on the y-axis, we now have a height versus position graph. We can go to the Customize tab. We can go to Series, press Trend Line, and Show R Squared. And then we're going to put a chart title on this and call it Height versus Position. We're going to do the same for the weight column and position. I'm going to call this one weight versus position, and we're going to give it a trend line with an R squared value. Now we can see that we have a weight versus position graph with an R squared value of 0.572 and a height versus position graph with an R-squared value of 0.688. What R-squared means is it's how much of the variation in position is explained by height or by weight. So for height, we can see that 68.8% of the variation in position can be explained with height. Now, to understand what the R-squared value truly means, we can put this data into a pandas data frame. And so we're going to hop into our IDE. Now, this might look intimidating at first, but we actually don't need to write any code to be able to make this work. We're going to use GitHub Copilot, and we're going to ask, how do I convert a CSV file to pandas data frame? But before we get to that, we're going to have to go back into our Excel spreadsheet, and we're going to have to download it as a CSV file so that we can work on it in Python. We're going to open the file path, and we're going to put it into the folder that we want. Let's rename it to NBA data, and we're going to cut it, put it inside of our NBA folder. And then we're also going to right click it, and we're going to copy as path. Now we go into our IDE, which I recommend VS Code because it makes it very easy to use GitHub Copilot with it. We're going to copy what code was just recommended to us and paste it into our IDE. And we're going to have to go back again, right click, and copy as path. And instead of this yourfile.csv, we're going to paste the path into here and delete the extra apostrophes. Now we're going to go File, Save, go down to the terminal. We're going to navigate to our file location, and then we are going to run the script. First, before you run the script, you might have to download the necessary libraries. So in this case, it tells us to import pandas as PD. If you want to download pandas, you go pip install pandas. And if this doesn't work for you, what I found works for me sometimes is I go py-m pip install pandas. And that will get you the pandas library if you don't already have it. But we can go py and say nba2.py in order to run our file. We get a syntax error. In this case, we can just highlight that syntax error, feed it back into Copilot, and see what it comes up with. And Copilot will recommend us 3 different ways of how to fix this error. We can go ahead and take the first one, copy it, and paste it right into our file. Now we can save and run our file once again. You can press the up key in order to access a previous command that you ran in the terminal. And now we can see that we have our data within pandas data frame. First thing we have to do is we notice that we have not a number. This pseudocode that we wrote earlier has to be deleted because we don't actually want that column to influence our data. So we're going to ask Copilot to remove last column of a data frame. We're going to copy paste what Copilot just gave us and overwrite this code. I'm going to save it and run it again. And now we can see that that last column, the pseudocode that we wrote, is now gone from the data frame. And we have all the data that we need within Panda's data frame, and we can start working on it. So now we're going to perform linear regression and look at what R-squared values we come up with within our Panda's data frame. Now when you're working with GitHub Copilot, you have to be very specific, both about the input data type and about what you want it to do. So we're going to say position is a numerical column with values 0, 0.5, 1, 1.5, or 2. Perform linear regression on the given data set for height versus position and weight versus position. Give the R-squared values of both models. And now GitHub Copilot is going to give us some code that will get us what we want. But we have to change the data frame value. So within our data frame, if we scroll up, we see that height is all caps, and Panda's data frame is case sensitive. So we have to change the lowercase height to uppercase height, lowercase position to uppercase position, and the lowercase weight to uppercase weight. Now we save this and we can run our data frame. And as you can see, we get an R-squared value of 0.68 and 0.61 for our height versus position and weight versus position models, which is quite similar to what we got within Google Sheets. Weight versus position is a little bit higher within Panda's data frame, but not too much so. Next, we are going to use our linear regression models to predict a player's position given their height or their weight. So what we're going to do is we're going to go to this scatter plot. We're going to say, given a player's height, let's say we know a player is 85 inches tall. What position do we expect that player to be? So we're going to go to our trend line, we're going to follow it up until we hit 85, and then we're going to round to the nearest half integer in order to predict their position. So at 85 inches, that is closest to 2.0 is the nearest half integer, and we would say that that player is most likely to be a center. So in order to do this, inside of Python, we're going to tell Copilot, predict position using the height and weight models for an arbitrary number of samples. Round to the nearest half integer. Reason why we're going to the nearest half integer is because we want to predict a position instead of getting a decimal like 1.778. We're going to want to round that up to 2.0 so we can predict it to be a center. Use random sampling for height and weight. Next, compare the predictions to real values of position and count the number of correct predictions. And we are going to copy paste the code that Copilot gives us. We have a new library that you might have to install called NumPy. Copy paste it into our IDE, save, and run our file again. Now you see that we have correct predictions using height model, 47 out of 100, and correct predictions using weight model, 42 out of 100. And because we used random sampling for height and weight, if we run this a couple times, we should get different values. See, now we have 46 and 43, 48 and 42. So we're going to get different values for the correct predictions using height and weight models, but we can see that our height model is consistently a little bit better than the weight model. So now we need something to compare these height and weight models to. So we're going to create two more predictions. First, we're going to randomly predict a player's position, and next we're going to predict a player's position based on the most common position in the NBA. So we're going to ask Copilot, find the most common player position. Going to copy paste that into here and run the code. And so now we see that the most common player position is 0.0, or the most common player position is a guard. And so we're going to say now randomly predict a player's position num sample number of times. Next, predict 0 for a player's position and count the number of correct predictions. It's going to give us code. We're going to copy and paste it into our IDE, save, and run. Now we have correct random predictions, 10 out of 100, and correct 0 predictions, 40 out of 100. And we can see that our height model is 45 and our weight model is 42. And this is random, so if we run it again, we'll get different values. Now we have 46, 43, 11, and 38. And so as you can see, our height and weight models do a lot better than the random predictions, which only get roughly 10 or 11 out of 100. But they only do a little bit better than the 0 predictions, which get 38, and that is just predicting that every player is a guard. So if we look at our Google Sheets, that would be like saying, no matter what height is given, we're going to predict a guard. So if we get a height of 70, we're going to predict the player to be a guard. If we get a height of 80, we're going to predict a guard. If we get a height of 85, we're also going to predict a guard. And so because the guard is the most common position in the NBA, you can predict every player to be a guard and still get a large percentage right. Now we're going to ask Copilot, what is the R-squared value of the model constantly predicting 0 for position? Now we're going to get code. We're going to copy and paste at the end of our script and find an R-squared value. And here's the R-squared value we get for that model constantly predicting 0, minus 1.15. So now we see that our zeros model gets a reasonable number of predictions correct, 38 out of 100, just by predicting that every player is a guard, and yet it has a rather terrible R-squared value of minus 1.15. So how is that possible? If we look at our Google Sheets data, our zeros model would be running along this axis here. It would be predicting 0 no matter if the player is 70 inches tall or 85 inches tall. And while it might get a reasonable number of predictions correct, it would do a terrible job of explaining the variation of player position within the data set. And so this trend line that we have, our line of best fit, is not optimizing for predicting a player position. Rather, it is doing its best job to explain the variation of player position given a player height. In other words, it is answering the question, what is the effect of changing player height on a player's position? And this R-squared value of 0.688 says that 68.8% of the variation in player position can be explained by the player's height. So now I leave this video off with a challenge for you. Now that you know that you can get a reasonably good prediction for a player's position simply by predicting every player to be a guard, can you modify the linear regression model for height and weight to get a higher number of correct predictions? Now, will this new model have an increased or a decreased R-squared value? Thank you for watching, and I hope that some of you will try this challenge out.